By the end of the 19th century, scientists were confident that they could fully describe the universe. They thought the cosmos was filled with a substance called ether. Light rays and radio signals were like waves in the ether, and sound was like compression waves in the air. All that was needed to complete the theory was to accurately measure the elasticity of the ether. In addition, when Jefferson's laboratory was being built at Harvard University, it was intentionally built without a single iron nail, so that accurate magnetometer research could be conducted in the future. Admittedly, the architects forgot that the red-brown brick from which the lab building and almost all of Harvard was constructed is rich in iron. The building is still in use, and Harvard doesn't know if the half of the library built without iron racks is good enough. But by the end of the century, there was widespread disagreement over the concept of ether. Light is expected to travel through the ether at a constant speed. But if you travel through the ether in the same direction as the light, its speed would appear to be slower, and if you travel in the opposite direction, it would appear to be faster. But the experiments that have been done have not confirmed this hypothesis. The most detailed and accurate experiment was conducted by Albert Michelson and Edward Morley of the GS School of Applied Sciences in Cleveland. In 1887, Michelson and Morley compared the speed of two rays of light perpendicular to each other. The Earth rotates on its axis and orbits the Sun. Therefore, the measuring instrument moves through the ether at different speeds and in different directions. However, Michelson and Morley found no difference in speed between the two lights. It did not accumulate over a day or a year. Light always seems to travel at the same speed relative to the observer, regardless of the observer and at what speed. Based on the Michelson-Morley experiment, Irish physicist George Fitzgerald and Dutch physicist Hendrik Lorentz hypothesized that the ether contracts and slows down bodies moving through clocks. The contraction and deceleration of the clock is such that the speed of light from the observer's point of view would always be the same, regardless of the direction in which it travels in the ether. Both Fitzgerald and Lorentz believed in the existence of the ether. In the Michelson-Morley interferometer, light from a source is split into two rays by means of an opaque mirror. The two beams are directed perpendicular to each other and then combined using another opaque mirror. If light propagates at different speeds in different directions, the maximum of the light wave of this first ray will reach a terminal point at the same time as the minimum of the light wave of the second ray, and these waves will neutralize each other. However, Einstein, in a paper written in June 1905, showed that the idea of an ether was not superfluous as long as the observer could not determine whether it was moving or not. Einstein began by saying that the laws of physics should be the same for freely moving observers. In particular, the measured speed of color must be the same for everyone, regardless of the speed of the observer. The speed of light is independent of their motion and is the same in all directions. To do this, the idea of universal time measured by all clocks had to be abandoned. Everyone has his or her own time. For two people, time is the same, both are at rest relative to each other, but are not in motion. This has been confirmed by several experiments, including an experiment with two accurate clocks that show slightly different times when flying in opposite directions around the world. That is, if you want to live longer, you should try to fly east so that the speed of the airplane adds to the speed of the Earth's rotation. However, the benefit in microscopic fractions of a second is more than offset by the harmful airplane food. Einstein's postulate that all laws of nature must be the same formed the basis of the theory of relativity of freely moving observers, so named because only relative motion is assumed to play a role. The beauty and simplicity of the theory of relativity convinced many thinkers, but it also had its detractors. Einstein proved two intangible 19th century axioms: the axiom of absolute rest, which is the law of the ether, and the axiom of universal time, which is measured by all clocks. A lot of people didn't like this. They questioned Einstein's theory that everything is relative and that there are no absolute moral standards in the world. Doubts about the theory of relativity continued throughout the 1920s and 1930s. Einstein won the Nobel Prize in Physics in 1921, but by Einstein's standards it was published in 1905. The motivation of the Nobel Committee did not mention the theory of relativity because it was considered too controversial. Today, however, the scientific community has fully accepted the theory of relativity, and its predictions have been verified by various experiments and used in modern technology. The most important result of the theory of relativity is the relationship between mass and energy. According to Einstein's postulate, the speed of light is always independent of the observer, and it is impossible to move faster than light. Here's why. When someone expends energy to accelerate an object, be it an elementary particle or a spaceship, the mass of that object increases, making it harder to accelerate. Now, normally the mass of a body remains the same, only its momentum increases, but the author's results are not affected. A particle cannot be accelerated to the speed of light because it requires infinite energy. Mass and energy are equivalent and equal to mc2, as shown in Einstein's famous equation E. Energy is equal to the product of mass times the square of the speed of light in free space. This is probably the physical equation. The basic meaning of this equation is that if a uranium nucleus decays into two nuclei with slightly less total mass, a large amount of energy is released. In 1939, shortly before World War II, several scientists who understood what this could lead to convinced Einstein to abandon his pacifist beliefs and radicalism, and signed a petition to Roosevelt to be sent to the United States Nuclear Research Program. The Einstein administration attached particular importance to this appeal. As a result, the Manhattan Project began and also carried out the bombs dropped on Hiroshima and Nagasaki in 1945. Einstein is sometimes blamed for this because he discovered the relationship between mass and energy, but that's like blaming Newton for crashing airplanes because he discovered gravity. Einstein was not personally involved in the Manhattan Project and was horrified when he heard about the atomic explosion. Although the theory of relativity is consistent with the laws of electricity and magnetism, it contradicts Newton's law of gravitation. According to this law, if you change the distribution of matter in some region of space, changes in the gravitational field are felt everywhere in the universe. This does not mean that signals can propagate faster than light, which rules out the theory of relativity. But it also requires the existence of absolute universal time. Otherwise, it is not clear what the moment is, which relativistic theory rejects in favor of local time. Einstein predicted this complication in 1907 when he was still working in Bernie's patent office, but did not think about the problem until 1911, when he moved to Prague. He realized that there was a close connection between acceleration and the gravitational field. An observer in a closed cabin, such as an elevator, does not know whether the cabin is resting in the Earth's gravitational field or being accelerated by a rocket in space. This was, of course, before the Star Trek era, so Einstein envisioned elevators, not spaceships. However, you can only accelerate your descent in an elevator for a short period of time, or else disaster will strike. If the Earth were flat, the apple might as well have hit Newton's head because of gravity or Newton's acceleration upward on the surface of the Earth. However, acceleration and gravity are not equivalent on a round Earth. People on opposite sides of the globe will accelerate in opposite directions, while remaining at a constant distance from each other. However, after returning to Zurich in 1912, an epiphany came to Einstein. He realized that the fields of velocity and gravity would remain equivalent if the geometry of Mendeleev's table were curved, even if not smooth as previously thought. According to Einstein, mass and energy compress time, but it remains to be seen exactly how. All bodies, apples, and planets try to move in space-time in a straight line, but their trajectories are curved by the gravitational field because space-time is curved. With the help of his friend Marcel Grossmann, Einstein studied the theory of curved surfaces and surfaces developed by Georg Friedrich Riemann in the mid-19th century. However, Riemann was only thinking about curved space. It took Einstein to realize that all time is curved. In 1913, Einstein and Grossman co-authored a paper in which they hypothesized that what we perceive as gravity is simply a reflection of curved space-time. But Einstein made a mistake. Error is inherent in human beings. That's why he and Grossman failed to derive equations relating the curvature of space-time to the mass and energy in it. Einstein continued to work on the problem in Berlin. The war did not affect him. He was relieved of his housework. In November 1915, he finally obtained the necessary formulas. In the summer of 1915, he visited Göttingen University, where he discussed his ideas with the mathematician David Gilbert. And it turns out that Gilbert had independently derived the same equations just a few days before Einstein. However, as Gilbert himself admitted, the honor of discovering the new theory belongs to Einstein. Page proposed to relate gravity to periodic perturbations. To Germany's credit, it must be said that it was in those years a very civilized country, because even during the war, the state did not prevent such scientific debates and communication between scientists. What was different about the fascist dictatorship that came 20 years later? The new theory of curved spacetime is called the general theory of relativity to distinguish it from the original theory, which said nothing about gravity. We call it special comparison. A remarkable confirmation of the theory of general relativity came in 1919 when a British expedition in West Africa observed a slight curvature of starlight passing through the sun during an eclipse. This was direct evidence of the coincidence of space and time, forcing us to radically rethink our view of the universe, which Euclid B.E.C. wrote the beginning of geometry. With his general theory of relativity, Einstein transformed space and time from passive entities in which events became active participants in the dynamics of the universe. This brings us to a large-scale problem that is also central to 21st century physics. The universe is full of matter, and matter bends over time, attracting each other. Einstein discovered that there was no solution to his equations describing a static universe that did not change over time. But he did not abandon the eternal and unchanging universe that had been envisioned for him and most of his contemporaries, but fixed the equation. A term called the cosmological constant was added, which turned back time so that bodies reversed their positions. The repulsive effect of the cosmological constant was supposed to balance the attraction of matter, and then the equations found a solution that allowed for a static universe. It was one of the biggest missed opportunities in the history of theoretical physics. Had Einstein stuck to the original equations, he would have predicted an expanding or contracting universe. In any case, no one took seriously the hypothesis that the universe was changing over time. But in the 1920s, sensational observations were made with the Mount Wilson Observatory's 100-inch telescope. These observations show that the farther away other galaxies are from us, the faster they are moving away from us. The universe is expanding. Moreover, the distance between any two galaxies is constantly increasing with time. This discovery made the cosmological constant unnecessary. It turns out that Einstein's equations don't necessarily have a static solution. Einstein later called the cosmological constant the biggest mistake of his life. These days, however, it doesn't seem to be a mistake at all. Recent observations discussed in Section 3 suggest that a small cosmological constant may be required. The general theory of relativity has completely changed the debate about the origin and fate of the universe. A static universe could have always existed or emerged in the past in its present form. But if galaxies are moving away from each other, it means they were closer together. About 15 billion years ago, they piled on top of each other, and the universe was very dense. The Catholic priest, Georges Lemaitre, who first studied this initial state of the universe, called it the primary atom, now known as the Big Bang. Einstein never seems to have taken the Big Bang theory seriously. He apparently believed that the simple model of a uniformly expanding universe would collapse if you traced the movements of galaxies backwards, and that galaxies also move outward at low speeds, allowing them to avoid collisions. He suggested that the universe may have undergone a compression phase, and that the jump to its current expansion occurred at moderate densities. However, we now know that nuclear reactions in the early universe had to have a density of at least 10 tons per cubic inch, or about 600 kilograms per cubic centimeter, to produce the amount of light elements we see in the universe and temperature, 10 billion degrees. In addition, a study of the cosmic microwave background radiation showed that the density was once trillion 1 and 72 tons per cubic inch. Moreover, we now know that Einstein's general theory of relativity does not allow for a transition from the universe's compression phase to its current expansion phase. As described in Chapter 2, Roger Penrose and I were able to show that the general theory of relativity predicts the origin of the universe. Consequently, Einstein's theory shows that time began. Einstein himself didn't like it, though. He refused to accept that general relativity could predict the death of massive stars. When they die, they can't generate enough heat to balance the power of their forces that are trying to crush them. Einstein believed that such stars go into some kind of stable final state. But today we know that stars with masses greater than 2 solar masses do not have a final state. Such stars continue to collapse and turn into black holes, regions of space-time so distorted that not even light can leave them. Penrose and I have shown that the general theory of relativity stops inside a black hole, both for the star itself and for the hapless astronaut who lands on it. However, neither the beginning nor the end of time are points at which the equations of the general theory of relativity do not work. Thus, the theory does not predict what will happen as a result of the Big Bang. Some see it as a manifestation of God's will, saying that God willed and created the universe. But there are others, including myself. Who would have thought that just because the universe was created, it should be subject to the same laws that apply to the rest of time? We have made some progress in the direction described in Chapter 3, but we still don't fully understand how the universe came into being. The general theory of relativity fails with the Big Bang because it contradicts the quantum hypothesis, the second major conceptual revolution of the early 20th century. The first step toward the quantum hypothesis was taken in Berlin in 1900, when Max Planck discovered that the radiation of a glowing body could be explained only by the fact that light is emitted and absorbed only in discrete parts called quanta. Einstein, in one of his seminal papers written while working in the patent office in 1905, showed that Planck's quantum hypothesis explained the photoelectric effect. Some metals give off electrons when exposed to light. Modern light detectors and television cameras are based on the photoelectric effect. Einstein was awarded the Nobel Prize in Physics for this work. Einstein continued to develop his quantum hypothesis in the 1920s, but he was deeply concerned with the work of Werner Heisenberg in Copenhagen, Paul Dirac in Cambridge, and Erwin Schrödinger in Zurich, which resulted in a new picture of reality, quantum mechanics. The original particles lost a certain position and velocity. The more precisely the position of an object can be determined, the less precisely its velocity can be determined, and vice versa. This randomness, the unpredictability of the basic laws of nature, frightened Einstein, and he wasn't in complete agreement with quantum mechanics. He expressed his feelings in the famous aphorism that God does not play ball. However, many scientists recognized the validity of the new quantum laws as they could explain several mysterious phenomena. Moreover, they have been well confirmed by observations. The laws of quantum mechanics underpinned modern concepts of chemistry, molecular biology, and electronics, and laid the foundation for technological advances that changed the world over the next half-century. In December 1932, realizing that the Nazis, led by Hitler, were rising to power, Einstein left Germany. 4 months later, he renounced his German citizenship and spent the last 20 years of his life at the Institute for Advanced Study in Princeton, New Jersey. At the same time, the Nazis in Germany began a campaign against Jewish science, repressing many Jewish scientists. This is partly why Germany never succeeded in building the atomic bomb. One of the main targets of this campaign was Einstein and his theory of relativity. When the book 100 Authors Against Einstein was published about Einstein. Why did it become so popular? If I'm wrong, one will suffice. After World War II, Einstein urged members of the anti-Hitler coalition to form a world government to control nuclear weapons. In 1948, Einstein was offered the presidency of the newly formed State of Israel, but he declined. He once remarked that politics is temporary, but formulas are eternal. The formulas of the general theory of relativity are the best epitaph for Einstein and the best memory of him. They will live on like the universe itself. Never in history has the world changed so much in 100 years. It is not about new political and economic doctrines, but about the rapid scientific and technological progress made possible by advances in fundamental physics. The most appropriate symbol of this progress is Albert Einstein, the twin paradox. According to the theory of relativity, each observer measures time differently. This is called the twin paradox. One of the twins, A, goes into space and travels at close to the speed of light, while his brother B stays on Earth. Because of A's motion, time moves slower on the spaceship than it does from the twin's point of view on Earth. So, upon his return, space traveler A2 will discover that his brother B2 is now older than he is. At first glance, this seems counterintuitive, but several experiments have shown that in such a case, the traveling twin will actually turn out to be younger. Einstein's prophetic letter to President Roosevelt, 1939. Thanks to the work of Galileo in France and Fermi and Szilard in America, the possibility of starting a nuclear chain reaction in large masses of uranium has been discovered in the last 4 months. Many new elements such as radio. This will almost now be accomplished in the near future. This new phenomenon will also lead to the creation of bombs, and it can be assumed, though with little certainty, that very powerful new types of bombs will be created in this way. The binding energy of atoms. Atomic nuclei are made up of protons and neutrons that are held together by a strong force. However, the mass of a nucleus is always less than the sum of the masses of its constituent protons and neutrons. The difference in mass serves as the binding energy of the nucleus, which holds the nucleus together. This energy can be calculated using Einstein's formula. The binding energy of a nucleus is c squared times dm, where dm is the difference between the mass of the nucleus and the sum of the masses of its particles. Nuclear explosive devices are extremely destructive because of the release of this potential energy. Chain reaction. A neutron produced by the decay of a U-235 nucleus collides with another nucleus. As a result, this nucleus also decays and sets off a chain reaction of further collisions. If the reaction is self-sustaining, it is called a critical reaction, and the mass of V235 is called the critical mass. Chapter 2. The shape of time. Einstein's general theory of relativity gives the shape of time. How can this be reconciled with quantum theory? What is time? As the old song goes, a constant stream carrying all dreams into the past, or something like a railroad. What if it had rings and branches? Then you could move forward, but you would find yourself back at the previous stage, in the same branch. The 19th century English poet Charles Lamb wrote, "There is nothing more mysterious to me than space and time, but time and space forget me least of all, because I never think of them. We always forget about space and time and what they mean, but we sometimes wonder what time is, where it began, and where it is taking us. It seems to me that any scientific theory, not a theory of time, must be based on the most reliable and constructive principles of the philosophy of science, the positivist views of Karl Popper and other philosophers. According to their worldview, a scientific theory is a mathematical model that describes and systematizes the observations we make. A good theory describes many phenomena with a few simple postulates, is concrete and testable. If the prediction agrees with the observations, the theory stands up to scrutiny. But it is impossible to prove. On the other hand, if the observations do not agree with the prediction, the theory should be rejected or modified. At least that's the way it should be. In practice, theorists often question the accuracy of the observations as well as the reliability, the moral and ethical qualities of the observers. If someone like me holds a positivist viewpoint, there is no way to tell what time it is. You can cite some mathematical model of time that scientists think is pretty good, and tell us what predictions it makes. The first mathematical model of space and time was published by Isaac Newton in 1687 in his book The Mathematical Beginnings of Natural Philosophy. Newton held the position of Lucas Professor of Mathematics at Cambridge, which is the same chair I am in now, which of course at that time was not equipped with any electronics. According to Newton's model, time and space serve as a backdrop for events that do not affect anyone. Time is independent of space, and a single line viewed as a railroad stretches infinitely in both directions. Time itself is eternal. It always has been, and always will be. On the other hand, many of Newton's contemporaries believed that the physical universe in its present state was created only a few thousand years ago. This inconsistency troubled many philosophers, including the German thinker Immanuel Kant. If the universe was indeed created, why wait forever before it was created? On the other hand, if the universe has always existed, why hasn't everything that was supposed to happen happened yet? Why is history incomplete? In particular, why doesn't the universe exist? That is, not all objects have become the same temperature. Kant called this problem the antinomy of pure reason, because I see here a logical contradiction that cannot be resolved. However, such a contradiction arises only within the framework of Newton's mathematical model, according to which time is an infinite line, independent of what happens in the universe. At the same time, we know from the first chapter that in 1915 Einstein proposed a new mathematical model, the theory of general relativity. Since the year Einstein's paper was published, we embellish his theory with various bows and curlicues, but our model of spacetime is based on what Einstein proposed. This and the following chapters describe how our ideas have evolved since the publication of Einstein's revolutionary paper. It is the success story of many scientists, and I am proud of my modest contribution. The general theory of relativity adds one dimension to the three dimensions of space, called spacetime. This theory also describes the effect of gravity. The distribution of matter and energy in the universe distorts and complicates time, resulting in a non-planar structure. Such periodic objects move in a straight line, but because of the periodic curvature, their trajectory is curved, and they move as if under the influence of a gravitational field. Let's use a crude analogy. Don't take it literally. Imagine a rubber sheet. Now let's put a big ball on the table. That would be our sun. Under the weight of the ball, the sheet will bend around the sun. If you now roll small balls onto the sheet, for example, from a tray, they won't roll straight off the sheet, and will revolve around a heavier object, such as the planets around the sun. This analogy is incomplete because space is two-dimensional, the rubber surface is curved, and time remains constant, as in Newton's theory. However, according to the theory of general relativity, time and space are closely related, as confirmed by many experiments. It is impossible to curve space without affecting time. So there is a form of time. By warping space and time, the general theory of relativity transforms them from a passive background in which events become active, dynamic participants. As for Newton's theory that time is independent of anything, it would be reasonable to ask what God was doing before he created the universe. According to St. Augustine, this is no reason to joke that hell is made for those who dig too deep. This is a serious question that has been pondered over for centuries. According to St. Augustine, God created nothing before he created the heavens and the earth. This is actually very close to modern views. On the other hand, according to the general theory of relativity, time and space are related to each other and to the universe in which they exist. They are defined on the basis of measurements of some parameters of the universe. For example, the number of vibrations or the length of a ruler in a quartz watch crystal. With this definition of time, it is easy to imagine that there must be a minimum or maximum value in the universe. That is, a beginning or an end. It is pointless to ask what happened before the beginning or the end because that is beyond the scope of the definition of time. Of course, it was important to understand whether the mathematical model of the general theory of relativity predicted the beginning or the end of the universe. In general, theoretical physicists, including Einstein himself, abandoned the belief that time extends infinitely in both directions. Otherwise, pesky questions about the creation of the universe began, apparently beyond the scope of science. On the other hand, if the universe has always existed, why hasn't everything that was supposed to happen happened yet? Why is history incomplete? In particular, why doesn't the universe exist? That is, not all objects have become the same temperature. Kant called this problem the antinomy of pure reason, because I see here a logical contradiction that cannot be resolved. However, such a contradiction arises only within the framework of Newton's mathematical model, according to which time is an infinite line, independent of what happens in the universe. At the same time, we know from the first chapter that in 1915 Einstein proposed a new mathematical model, the theory of general relativity. Since the year Einstein's paper was published, we embellish his theory with various bows and curlicues, but our model of space-time is based on what Einstein proposed. This and the following chapters describe how our ideas have evolved since the publication of Einstein's revolutionary paper. It is the success story of many scientists, and I am proud of my modest contribution. The general theory of relativity adds one dimension to the three dimensions of space called space-time. This theory also describes the effect of gravity. The distribution of matter and energy in the universe distorts and complicates time, resulting in a non-planar structure. Such periodic objects move in a straight line. But because of the periodic curvature, their trajectory is curved and they move as if under the influence of a gravitational field. Let's use a crude analogy. Don't take it literally. Imagine a rubber sheet. Now, let's put a big ball on the table. That would be our sun. Under the weight of the ball, the sheet will bend around the sun. If you now roll small balls onto the sheet, for example, from a tray, they won't roll straight off the sheet, and will revolve around a heavier object, such as the planets around the sun. This analogy is incomplete because space is two-dimensional, the rubber surface is curved, and time remains constant, as in Newton's theory. However, according to the theory of general relativity, time and space are closely related, as confirmed by many experiments. It is impossible to curve space without affecting time, so there is a form of time. By warping space and time, the general theory of relativity transforms them from a passive background in which events become active, dynamic participants. As for Newton's theory that time is independent of anything, it would be reasonable to ask what God was doing before he created the universe. According to St. Augustine, this is no reason to joke that hell is made for those who dig too deep. This is a serious question that has been pondered over for centuries. According to St. Augustine, God created nothing before he created the heavens and the earth. This is actually very close to modern views. On the other hand, according to the general theory of relativity, time and space are related to each other and to the universe in which they exist. They are defined on the basis of measurements of some parameters of the universe. For example, the number of vibrations or the length of a ruler in a quartz watch crystal. With this definition of time, it is easy to imagine that there must be a minimum or maximum value in the universe, that is, a beginning or an end. It is pointless to ask what happened before the beginning or the end because that is beyond the scope of the definition of time. Of course, it was important to understand whether the mathematical model of the general theory of relativity predicted the beginning or the end of the universe. In general, theoretical physicists, including Einstein himself, abandoned the belief that time extends infinitely in both directions. Otherwise, pesky questions about the creation of the universe began, apparently beyond the scope of science. There were specific solutions to Einstein's equation that indicated whether time had a beginning or an end, but all of these were reduced to special cases requiring great symmetry. In a real material body collapsing under its own gravity, pressure, or lateral velocity, it was assumed that all the work would prevent it from falling to a single point of infinite density. Similarly, if we trace the expansion of the universe backwards, matter in the universe should not have arisen from a point of infinite density. This type of thinking has come to be called unity. It could be the beginning or the end of time. In 1963, two Soviet scientists, Eugene Lifshitz and Isaac Kalatnikov, announced that they could prove that a solution to Einstein's equations with singularity might require a special relationship between matter and velocity. The probability that a solution describing the universe fully satisfies this relation is almost zero. Almost all solutions that could describe the universe would avoid an infinite density singularity. Before the expansion of the universe, there would have to have been a compression phase, during which matter condensed but did not compress infinitely, and then began to fly away again, which would mark the beginning of the current expansion phase. And in this case, time would go on forever, from an infinite past to an infinite future. But not everyone was convinced by Lifshitz and Kalatnikov's arguments. Roger Penrose and I chose a different approach, based not on a detailed study of the solution of the equation, but on the study of the global structure of space-time. Within the framework of the general theory of relativity, periodicity is warped not only by the influence of massive bodies, but also by the influence of the energy in them. Energy is always positive, so it forms a periodic curve that causes rays of light to bend into each other. Consider a cone of light backwards through space-time, formed by the trajectories of light rays from distant galaxies that reach us now. In a coordinate system where time is delayed on the vertical axis and horizontal on the horizontal axis, it is the top of the cone where we are. Going back in time, from top to bottom to the base of the cone, we see that galaxies existed earlier and earlier, because the universe was expanding and everything in it was very close together. Looking back, we see areas of higher density matter. We also see faint microwave background radiation coming to us through the light cone when the universe was denser and hotter than it is now. If we tune receivers to different frequencies of microwave radiation, we can measure its spectrum. See the power distribution over frequency, and that this spectrum is typical of radiation from a body at a temperature 2.7 degrees Celsius above absolute zero. Such radiation would not destroy the pizza. However, since its spectrum closely matches the character of radiation from a body at 2.7 degrees Celsius, it indicates that the radiation comes from regions of space inaccessible to microwaves. Thus, we can conclude that the passing light cone must have passed through some substance. This substance is enough to warp time, so the light rays in the passing light cone bend and converge. As we go deeper into the past, the cross-section of our light cone reaches its maximum size and then shrinks again. Our past is like a pear. As you pass by the cone of light, the density of positive matter energy causes the light rays to converge. The cross-section of the light cone will shrink to zero at the limit. This means that all the matter inside the light cone will be in the region where the boundary is zero. Many physicists did not like the idea of the beginning and end of time. Therefore, they pointed out that such a mathematical model could not be expected to describe well the periodicity around unity. The classical theory of general relativity, which describes gravitational interactions, therefore does not account for the uncertainty introduced by quantum theory, which governs all other interactions we know. This discrepancy almost never plays a role in the universe because the scales at which periodic curvature arises are too large and the scales at which quantum effects must be accounted for are too small. However, near unity, these scales become comparable, so quantum gravitational effects begin to play an important role. Thus, Penrose and my singularity theorems have established that the classical domain of spacetime is intimately connected to the past and possibly the future through domains that must account for quantum gravity. To understand the origin of the universe and to know what lies ahead, we need a theory of quantum gravity. And that's pretty much the case with the book you're listening to. Quantum theories of systems like atoms, made up of finite particles, were formulated in the 1920s by Heisenberg, Schrödinger, and Dirac. However, when scientists tried to extend the ideas of quantum mechanics to Maxwell's equations describing electricity, magnetism, and light, they were initially unsuccessful. In 1865, British physicist James Clerk Maxwell reconciled all known laws of electricity and magnetism. Maxwell's theory relies on the existence of fields that transmit motion from one place to another. Maxwell realized that fields propagating electric and magnetic disturbances are dynamic objects capable of oscillating and moving through space.